first a couple of announcements. The office hours for this course will be on Tuesday and Thursday in Earth Science Building 4109 from 1 to 2:30. If these times are inconvenient for you, just send me an email, we'll try to schedule an appointment. The midterms will be during the lectures on February 7 and March 19. One of them is Thursday lecture, the other one is Tuesday lecture. So make sure that you can come to these lectures. The grading scheme, well, it's not decided precisely yet. We haven't decided how long the homeworks will be and how much weight they will carry. We'll decide probably by this Thursday. But in general, it will be 2 midterms, final, and bi-weekly homework. So roughly bi-weekly. So we'll allow about 2 weeks interval between the homeworks. And hopefully I'll give you the first one this Thursday, not the coming Tuesday. Also, well, some people have issues with registering and maybe have missed the first lecture. You can watch the video for the first lecture here. You can go to this website and there is a link to the video of the first lecture. And in general, I will try to record every lecture and put it online. Okay, so this is the announcements. Maybe any questions about anything in general? Okay, so let me remind you what we did last time. We talked about what is linear programming in general, what kind of problems is it trying to solve. We had an example of a linear programming problem, and so we didn't really talk about how to actually solve them. Let me remind just what are linear programming problems. So linear programming problem is any problem of the following form: maximize or minimize a linear function subject to linear constraints, which can be linear equalities or linear inequalities. So if you recall, linear function is something like number times a variable plus a number times another variable and so on. Linear constraint is when a linear function is either equal to a number, smaller than a number, or bigger than a number. So these kind of problems. Also maybe, well, just to make sure that I'm completely precise, subject to finitely many linear constraints. You don't want infinitely many of those. So let me give you an example. Something like this: minimize the function 5x1 minus 7x2 plus 3x3 subject to minus 2x1 plus 3x2 minus 5x3 is greater or equal to 3. x1 minus x3 is equal to 5. x1 is positive, x2 is positive, x3 is positive. So maybe some problem will, I don't know from what kind of domain, but in the end it translates to the following mathematical problem. Find the minimal possible value of such function subject to these constraints. And this is a typical linear programming problem. It is about minimizing a linear function, number times variable plus number times variable plus number times variable, subject to linear constraint, linear inequality, and linear equality, and another 3 linear equalities. In the very end, we started to talk about linear programming problem in standard form. So we talked that it's somewhat important to translate all kinds of problems to some pretty standard form for several reasons. One is the algorithm that we are going to present will work only for problems in standard form. Another reason, well, you might want to take this problem and ask the computer, well, dear computer, please ask me to solve such a problem. And then you will have to give it, well, some input. So you want to establish some protocol. You want to say, my input will mean the following problem. The numbers that I enter will mean the following things. And then we have such a thing, linear programming problem in standard form. And this is a more restricted class. It's only about maximizing still a linear function subject to constraints of the following form. Linear function is smaller or equal than a number. We only allow inequalities, and only inequalities is smaller or equal. Well, maybe several of those. And another one like this. Several of those, and also all variables positive. So let me give you an example of such a thing. Something like this. Maximize (5x1 plus 3x2) subject to x1 minus 3x2 smaller or equal than 5. x1 is positive, x2 is positive. So this problem, even though it's a linear programming problem, it's not in the standard form. It is about minimizing the function, not maximizing. It is about inequality in the opposite direction, not like this. It also contains some equality, which you don't want in a problem in standard form. Well, this is not a problem in standard form. This one is. It has all the requirements. It's about maximization, all the inequalities, all the constraints are inequalities with small or equal sign, and all the variables that appear in the problem are positive. So that's what's called linear programming problem in standard form. We'll have an explanation for why the standard form is good and why our algorithm will only work for problems in this kind of form. But before we even go there, let's discuss, well, we do want to solve such kind of problems as well. But we will have a solution which will work only for this kind of problems in standard form. So is there a way to translate this problem to one in standard form? Okay, so let's go step by step. What's wrong with this one? What makes it not a problem in standard form? First thing, minimize instead of maximize. So any suggestions? I want to translate a problem about minimizing something to a problem about maximizing something. Yeah?
Just link that to the negative?
Yes, exactly. So, translation of, well, let's say, that problem to standard form. So first idea, instead of minimizing a quantity, I'll maximize its negative. So the smaller the quantity, the larger is its negative. So my problem will be about maximizing now minus 5x1 plus 7x2 minus 3x2. Good. So now my problem is about maximizing the function. Next I have an inequality, but unfortunately it's the wrong way. It's not something smaller than 3, it's something bigger than 3. What to do about this one? Do the same thing, yes. So I know that if something is bigger than 3, it's the same as saying that minus this is smaller than minus 3. So translate this inequality to 2x1 minus 3x2 plus 5x3 smaller or equal than negative 3. Okay, next one might be a little bit trickier. I have equality, but in this kind of problems I do not want equalities. What to do about this one?
Can we substitute that into the equation and get rid of one word?
Okay, yes. So that's a really good idea. So one possible, there are several kind of standard solutions what to do in this case. One standard solution is, well, here we have equality. It means that we can express one of the variables in terms of the other, in terms of the other ones. Well, let's express it, substitute into all the other inequalities and get a new problem which, well, has one variable less. It's even simpler. So, ideas about x1 minus x3 equal to 5. First idea is like this. Use x1 which is equal to x3 plus 5. I express one of the variables in terms of the others and plug into other inequalities. We'll do this in a second. It's a really good idea because, well, it simplifies the problem. Instead of problem with 3 variables, we'll have now a problem with 2 variables, which is good. But if we are really lazy and, well, if we are using the computer or something like this and we don't care about how complicated the problem becomes, well, here's another idea. Maybe somebody else has another idea without eliminating the variable.
You could express it as 2 inequalities.
Yes, exactly. So one equality is the same as 2 inequalities. One is that this quantity is bigger than 5, another one is smaller than 5. So replace by 2 inequalities. x1 minus x3 is bigger or equal than 5. x1 minus x3 is smaller or equal than 5. Well, there is a small problem. This inequality is not in the standard form, but we already know what to do. Just write that it's minus x1 plus x3 smaller or equal than minus 5. So this should be replaced by minus x1 plus x3 smaller or equal to negative 5. And now we have, well, a problem in standard form. We have this inequality, together they imply this equality. We have this inequality and we want to maximize this. And also we had, to start with, we already had all the variables positive, so it's good. Well, let's actually carry out this first step, this first idea. You see, using the second idea, we got still a complicated problem. We got a problem with 3 variables, lots of inequalities. It's usually quite hard. Using the first idea, we will simplify this problem and actually we will be able to solve it. So, let's use idea number 1. So use the fact that x1 is x3 plus 5. And now I want to once again translate everything, but now without x1. I want to maximize minus 5 times, instead of x1 I write x3 plus 5 plus 7x2 minus 3x3 subject 2, and the constraints will be 2 times x3 plus x5 instead of x1 minus 3x2 plus 5x3 smaller or equal to negative 3. And I still, well, the second constraint is automatic. I used it here, but I still have these 3 constraints. All the variables are positive. I'll have to rewrite those. First one, x1 is bigger than 0, translates to x3 plus 5 is bigger or equal than 0. Second one stays as it is, and the last one stays as it is. So every time I saw x1, I just replaced it by x3 plus 5. Very kind of automatic procedure. Well, let's open the brackets, let's rewrite this problem. Maximize minus 5x3 minus another 3x3, so minus 8x3 plus 7x2 and minus 25. And subject to 2x3 plus 5x3 is 7x3 minus 3x2 plus 10 smaller or equal to negative 3. x3 is bigger or equal to negative 5. x2 is positive. x3 is positive. Okay, is this problem a linear programming problem in the standard form? Why not? Okay, this one is, well, yes, it is a problem, but it's easy to solve. So instead of this inequality, well, we actually have two ways to solve it. So this is a problem. One way to solve it is our standard form, standard trick. Instead of bigger or equal, let's multiply both sides by minus 1. Rewrite it as minus x3 smaller or equal than 5. That's one idea. And let me write as we did before, that's first idea. Do you have any other idea how to eliminate this problem?
Basically, use just variable x3 minus 5. That will be equated to.
Well, x3 plus 5, that's x1.
Oh.
So we'll reintroduce x1, which is not good.
Isn't that better? Because then x1 will be greater than 5 and it will be positive.
Okay, so here we have we don't have to reintroduce x1 to see that this idea is useful. We already have a redundant condition. It is bigger than minus 5, but it also is bigger than 0. So this is actually redundant. We have x3 bigger or equal than 0. So if you want to save, well, space-time energy, let's just remove this inequality. Let's not convert it to an inequality in standard form, let's just remove it. It's not necessary. We already know that x3 is positive. We require this. Requiring that it's bigger than negative 5 is automatic. So this is not a problem. We can just cross it out. Are there any other problems? Is this now a problem in standard form?
Or should we move all the constants to one side?
Yes, so there is a small problem. In linear programming questions, in linear programming problems, we want to maximize the linear function. Well, a linear function. It's number times variable plus number times variable. Nothing about plus a number. So this part is not good. This minus 25 is not good. On the other hand, it's very easy to eliminate. Maximizing this thing minus 25 is the same thing as just maximizing this thing alone. So let's do this. So finally, we'll translate this to a problem in standard form. In standard form. Maximize minus 8x3 plus 7x2. Now I forget about this minus 25 because it doesn't matter whether I subtract the minus the 25 or not. Subject to. And indeed I want to move the constants to the side with the constants. So subject to 7x3 minus 3x2 smaller or equal to negative 13, x2 positive, x3 positive. Now it is in standard form. If you want, it's kind of a checklist. Is it about maximization? Yes. Is it about maximizing a linear function? Yes. Are all the constraints linear functions smaller or equal than a number? Yes. And are all the variables positive? Yes. Okay, so this is a linear programming problem in standard form. Okay, next step. Let's solve it. This problem is so simple that it's actually quite easy to solve it by hands. There is nothing complicated required to solve it. So maybe let's try to produce at least some assignments of numbers to x2 and x3 that will satisfy these constraints. So some positive numbers, such that 7 times the first one minus 3 times the second one is smaller than negative 13. And we'll see how large we can make this function. So any ideas? Yeah?
Take x3 equals 0.
x3 equal to 0. Okay, it's a good idea. It looks like a good idea because you see in this function x3 comes with a negative sign, so maybe it's a good idea to take x3 to be quite small. Also here, well, if I make x3 smaller, it only makes this inequality better. So first idea, take x3 equal to 0. Okay, that's not it. That's not the end of the story. I also want x2. So what can I do? What can I take?
Make it as large as you want.
Yes, basically yes. So, I mean, there are some values which I cannot take. Say, I can take x2 equal to 1. That won't satisfy this constraint. We'll have 0 minus 3, well, still too large. But if I increase x2, this inequality will become true. So if x2 is big, say million, I will have minus 3 millions. Well, obviously it is smaller than negative 13. What about this objective function? Well, it will only become larger. x2 will become large, 7 times x2 will become large. x2 really large. And then we are able to produce any kind of, well, we can make this objective function as large as we wish. So we can make the objective function as large as we wish. By just doing this, making x2 very large, and then we can make the whole function very large, and still satisfy the constraints. So such a problem is called unbounded. It does not have an optimal solution. I mean, we can make this function as big as we want. Well, typically what it means is, well, somebody didn't tell us about the constraint. I mean, usually, in practice, problems tend to have some optimal solution. So in practice, we can't make a perfect infinitely large typically. So I write this thing, kind of definition of the word unbounded. Well, such a problem is called unbounded. By such a problem, I mean one can make the objective function arbitrarily large. But of course, still satisfying the constraints. It's it's very important to satisfy the constraints. Okay, good. So now we know one reason why a problem might not have an optimal solution. It might have no optimal solution just because you can increase the objective function as you wish. It's not the only possible problem. So before we are going to solve actual problems which do have some optimal solutions, and we'll try to actually find the optimal solution, let's consider another example, which we'll also be able to solve by hand. The example will be maximize 100x1 plus 200x2 subject to the following things. x1 plus twice x2 is more or equal than 3. 2 times x1 plus x2 is more or equal than negative 3. x1 plus x2 is bigger or equal than 1. So maybe let's practice a little bit this notion of a problem in standard form. Is this one a problem in standard form?
No.
Why not?
Variables are probably.
Okay, yes. So, very important thing, a problem in standard form has to have all variables positive. This problem does not require x1 to be positive, x2 being positive. Well, there is a smaller problem which is easy to correct this inequality, but well, we know how to correct this. But this problem does not require the variables to be positive, it's not in the standard form. Okay, but anyway, it's quite easy to solve this. So, does anyone see a solution?
Can you pull it up a little bit?
Oh, yes, sure. Try this. Here, say x2 equal to 1, x1 equal to 0. Let's see. So, second constraint is not satisfied. Okay, so this didn't work. Any other solution? Okay, is there a reason why you're silent? Is there a solution? So I start to suspect that this problem has actually no solutions. Can you convince me that I'm right, or convince me that I'm wrong?
Okay, so if you add first two constraints, you get 3 times x1 plus x2 is less.
Okay,
less
yes.
than 0.
Let's add up the two constraints. 3 times x1 plus 3 times x2 is more or equal than 3 minus 3, which is 0.
That contradicts. So
Exactly. But I also want x1 plus x2 to be bigger than 1. Well, that's impossible. Impossible. So this problem has no solutions. So once again, let me introduce some words. So once again, some definitions. These definitions are just about introducing some terminology, standard terminology, and well, we have to deal with it. So a definition, an assignment of numbers to the variables that satisfies the constraints is called a feasible solution. So every time you have some assignment of numbers to the variables, and this assignment does satisfy the constraints, we don't just call it a solution, we call it a feasible solution. Once again, we won't have a reason for adding an extra adjective here, kind of what kind of solution would be. I mean, if it is a solution, it should satisfy the constraints, kind of strange, but later we will have kind of solutions which do not satisfy the constraints, and we'll actually need this extra word. So for now, let's just accept that a solution to such a problem is called a feasible solution. And such a problem with no feasible solutions is called infeasible. Okay. Now we have two possible reasons why a problem might have no optimal solution. One is it has no solutions at all. Another reason, it has too many of those. There are so many that you can make the target function, the objective function, as large as you wish. So infeasible problems or unbounded problems. Both have no optimal solutions. Well, next question is very natural. Are these all possible reasons why a problem might have no optimal solution? And it turns out that yes. In linear programming, these are all the reasons. So just write it down, write down the statement, and explain that it's interesting. So claim problem is, well, a linear programming problem is either infeasible or unbounded or has an optimal solution. So first of all, what is it saying? It says that every linear programming problem belongs to one of the classes. Exactly one of the classes. It's either infeasible, which means it has no solutions, or it has enough solutions so that you can make the target function, objective function, as large as you wish, or it has one solution which gives the largest value of the objective function, optimal solution. From the first glance, the statement looks obvious. I mean, trivial. Just nothing there. I mean, what could happen? You have a problem of maximizing a function on a given domain, given inequalities. Well, what could be the problem? You want to find the largest value of the function. One thing that could go wrong, the domain could be empty. There might be no solutions. Well, that's this case. If there is at least one solution, well, you can either, well, you have now at least one solution, you have the value of the objective function at this point, well, some attempt at finding the maximum. Then you have, well, you might have more than one solution, you might have several of those, well, go over all of those and try to find the largest. Either you will be able to go to infinity, or you will find the largest. Well, sounds plausible, but, well, actually it's not that obvious. And if you've taken calculus class, you know that in calculus it's not, first of all, not obvious, second thing, not true. So let me give you a kind of, so not true in general optimization problems. For instance, here's a problem that does not belong to any one of these three classes. Maximize function which looks like this. So I'll just draw the graph and the logistic function. It goes from about, well, close to 0 at negative infinity to close to 1 at positive infinity, but never actually attains the values 0 and 1, well, on real numbers. So just impose no constraints on the variable. This problem has feasible solutions, of course. You can just take any value of the number of the parameter and you get a solution. It is bounded. All the values of the objective function are smaller than 1. But it has no maximum, no optimal solution. If you have a guess that the optimal one is here, you can go a little bit to the right and find one which is slightly bigger. So this statement is not empty, it's interesting. There is something there. And it's about our choice of function and our choice of constraints. So for linear functions on such domains, it is true. It is not true for non-linear functions. So we won't really emphasize proofs of such statements, but well, you should be aware that this is something. Okay, so now we have some terminology and some knowledge why the problem might not have a solution. So maybe any questions about this part? Because the next part will be how to actually find a solution. The optimal solution when it doesn't exist. Okay, so now we start with the actually interesting part of the course, how to solve a linear programming problem. How to solve a linear programming problem. In standard form. And we'll start with an example. And we'll make, well, we have quite enough time to do it slowly. We'll start with an example, then we'll formalize what we're doing, then we'll try to optimize the steps, make less calculations. But for now, let's start with a simple example. Maximize, we'll have just two variables. So 3x1 plus x2, subject to x1 minus 2x2 smaller or equal than 2, 3x1 minus x2 smaller or equal than 11, x1 plus x2 smaller or equal than 9, x1 positive, x2 positive. So before we start solving the problem, let's make sure that it does have an optimal solution. We have to check, according to this claim, just two things. That there is at least one solution and that the problem is bounded. That you cannot make this function as large as you wish. So let's check the first one. Does this problem have at least one solution? It's really simple. We have just to find one assignment of numbers which will satisfy these constraints. Any ideas?
Take both variables equal to 1.
1. Okay, let's see. 1 minus 2 times 1 is smaller than 2. 3 times 1 minus 1 is smaller than 11. 1 plus 1 is smaller than 9. 1 is positive, 1 is positive. Okay, yes, it works. problem is feasible. A feasible solution. X1 equal to 1, X2 equal to 1. So it does satisfy these constraints. We found, well, at least one solution. Maybe a good idea to keep in mind is, well, as a first step, it's a good idea to try to check whether 0, 0 is a solution. It just requires so few calculations that you can do it automatically, always. So in this case, is 0, 0 a solution? Well, yes. 0, 0 makes all the left sides 0 and the right sides are positive. So even simpler. X1 equal to 0, X2 equal to 0 is a feasible solution. But anyway, this was also would require just a little bit more calculations, but it was a feasible solution. Next is the problem 1. Is there a chance that I can make 3x1 plus x2 as large as I wish, subject to these constraints?
Should we test for 0 a really large number and a really large number 0?
Second.
Should we test for a really large x1 equals a really large number, x2 equals 0, and then
Okay, it might be a good kind of first step. If I try to take x1 very, very large and x2, let's say 0, well, what will go wrong?
The problem's bounded because of the second constraint, because their sum can't be more than that. And
The third constraint.
the third.
Okay, yes. So the problem with taking x1 to be infinitely large or very, very large and x2 equal to 0 is basically each one of these constraints will be violated. If x1 is large, well, we'll have large numbers smaller than 2, large numbers smaller than 11, large numbers smaller than 9. Well, maybe there is a chance to make x1 large and x2 kind of also large. Well, the first constraint might actually be true. If you have large number, the difference might be smaller than 2. Maybe x1 is 2 millions and x2 is 1 million. Then the left-hand side is 0, smaller than 2. Similarly, about the second constraint. There is a chance that x1 is large, x2 is large, but the difference is smaller than 11. But the third constraint gives me, well, quite a heavy bound. The sum must be at most 9. It means that each one of the variables, since it is positive, must be at most 9. So the answer is yes. From x1 plus x2 smaller than 9, well, and x1 positive, x2 positive, I can conclude that x1 is smaller than 9, x2 is smaller than 9, hence my objective function 3x1 plus x2 is smaller than 3 times 9 plus 9, so it's 36. So whatever solution I will ever find, the objective function will be smaller than 36. It's not to say that I can obtain 36. I didn't even try. Well, but whatever I'll get, the objective function will be smaller than 36. So basically, any constraint which has this property, all the coefficients of all the variables are positive, will make the problem bounded using the same argument. So it's a good idea to look for constraints of this form. Positive number times the first variable, positive number second variable, smaller than something. It always makes the problem bounded. It's not the only possible reason why a problem might be bounded, but it's the simplest. Okay. Next thing, we introduced the general algorithm. let's see whether the problem is complicated. Whether we can, or maybe we can guess the solution. Maybe, I mean, it doesn't look like this problem is too complicated. It has just two variables, and how complicated can be an assignment of two numbers to two variables. So let's try some guesses. So let's make it competition. So I want you to produce some feasible solutions which produce the largest possible objective function. The winner is, of course, the one with the largest value of the objective function. So, we have one solution. 1, 1, or let's say x1, x2 objective function, which is vx1 plus x2. And we had one attempt was like this: 1, 1, objective function is 4.
6, 3.
6, 3. Okay, let's see. 6, 3. The objective function is 3 times 6 plus 3, 21. Okay, second constraint, 3 times 6, 18, minus 3, 15. Okay, it doesn't work. So let's make this actually work. So 5, 1, let's see. The objective function, first of all, is 16. The variable, well, the constraints, 5 minus 2 times 1. First constraint doesn't work. So once again, no. 5, 4. 5, 4. Okay. So this is 5 times 3, 15 plus 4, 19. Let's see whether it works. 5 minus 2 times 4, yes. 15 minus 4, okay, exactly 11. And 5 plus 4 is 9. Okay, looks like it works. Is there a better solution?
No,
Why not?
because that one's pretty good.
Okay, that's a good reason.
Well, we kind of know we can get most 36. So
Okay.
maybe that's
But maybe somebody will find something like 20.
Yeah, you could simplify the constraint by changing the cosine. Because for a given x1, you have a maximum of x1.
Okay, so here's an idea. We noticed that in this solution, which was pretty good, these two constraints were not just, we pushed them to the very limit of these constraints. We made this exactly 11 and this exactly 9. Could we also push this constraint to its limit, to be exactly 2?
you would have 3 equations, 2 variables.
Aha, yes. So let's pursue this idea. We want to kind of push the constraints to their bounds. How many constraints can we push to their bounds? Well, the observation is we can choose exactly 2 constraints to push to their bounds. Why? Because once we have 2 equalities, we do have the values of the variables. 2 equations on 2 variables give you a solution, one solution. Okay, why did we choose these 2 constraints? Maybe a better idea would be to choose this one and that one, and try to push those to their bounds. Well, it actually might be. So let's try to solve the equation x1 minus 2x2 is 2, and x plus x2 is 9. So we'll solve it, we'll find the solution, we'll check whether the solution satisfies the other constraints. If it does, let's compute the objective function, and let's make another entry in this table.
Question, so we're assuming that x1 and x2 are integers, right?
No,
Or they can be
any numbers.
Okay.
So, well, before I go, well, I didn't announce it, but who made the suggestion of this solution? You? You did. Okay, so I didn't think that it will be so fast. It is the best possible solution. And second, yes. So here's the dice.
He made the suggestion, but I was the one who said that it's the best possible.
Oh.
Do you want it?
I can share.
Yeah, you can have it.
I mean, you can break it. Sure. So the idea to check that well, that it is an optimal solution. Well, our intuition suggests that it is a good idea to push these constraints to their bounds. That suggests solving well quite a bit of linear system of equations. How many of those? Well, we have 1, 2, 3, 4, 5 constraints. We might push to the bounds any 2 of those, which means 5 times 4 divided by 2, well, 10 systems of linear equations. So, one idea for solving such systems so first thing is just our intuition. We are better off pushing as many constraints as possible to their bounds. So why this intuition is
if it was like 3x1 minus x2 or something, then would it be better to not do that? Or is it still always best?
Actually, it is always the best. So let me try to explain why this intuition is actually correct. So you have a function over some domain, and this function is actually linear. So you should imagine that it is kind of like this. It is a function over a domain. If you are not on the very boundary of this domain, if you did not push to the very limit of your bounds, well, if you're inside the domain, you have a linear function. In some direction, it must be increasing still. And if you can move in this direction, you will increase the value of this linear function. So it does make sense that this works. Maybe, maybe this doesn't explain the fact that we want to push as many of the constraints as we want to the limit. But at least it explains that we want to push at least one of the constraints to its limit. Actually, it does explain why we might want to push as many of those to their limit. Suppose we are on the boundary, but well, we only encountered one of the constraints. Along this constraint, so maybe a good idea in this case would be to try to draw this region. This problem is two-dimensional, which means it's simple. I can draw a picture. So this domain, all possible pairs of numbers which satisfy these inequalities. Let me draw this. x1 is positive, x2 is positive. It means I'm in this polygon. x1 plus x2 is smaller than 9. Well, x1 plus x2 is 9 here and here. And x1 plus x2 is equal to 9 here. It is smaller than 9 in this domain. Another inequality. 3x1 minus x2 is smaller than 11. Well, x2 is 3x1 plus 11 is such a line. It's 11. 3x2 is minus 3x1. Okay, so it has 11 here, and it cuts this line at x2 is 0, 11 over 3, 11 over 3 is equal to this more than 3. So here. And we are talking about all the pairs of numbers where this is smaller than this, so we are talking about this region. So I think, oh, x, yes. Sorry. So it's x2 is 3x1, it's not minus. Okay, so it still passes through this point, but the slope is indeed positive, yes. So it looks like this. So this is x2 equals 3x1 plus 11. And we are talking about the region where this is smaller. It does contain, say, the origin. When x1, x2 is equal to 0, it is satisfied. So it is this region. This region. And this inequality, x1 is equal to, so x2 is x1 divided by 2, still a positive slope. x1, when x2 is equal to 0, x1 is equal to 2, and the slope is about 1/2. So this is 11 over 3, this is 2, and the slope is quite small. And we are talking now about this region.
I think the line you drew for x2 equals 3x plus 11 is actually x2 equals minus 11.
It's minus 11. And that's exactly what I wanted. Okay, yes. So this is like this. But that's, it is what I wanted. It is x2 is equal to 3x1 minus 11. And this one is, oh, x2 is equal to, let me just write x1 minus x2, 2x2 is equal to 2. And I hope that it is the correct one. And I want the set of points which satisfy all the constraints. So I don't want the points here, I don't want the points here, here, or here. I want only the points in this kind of polyhedron. It's pentagon, 5 sides. So I'm talking about all possible pairs of x1, x2 which are in this region. And over this region I have a linear function, 3x1 plus x2. You should imagine, well, the graph of this function is some linear function like this. It actually passes through the origin, so probably like this. And well, we might try to imagine how it actually looks like this, like this. It might be a little bit hard. But anyway, it is some kind of plane lying over this region. Now, why do I want to push the constraints to their bounds? Well, the reason is, if I'm inside this region, if I did not push any of the constraints to their bounds, well, I have a linear function in one of the directions it's increasing, I will move in this direction. Okay, suppose I suspect that my best solution is here. I push just one of the constraints to this one. Well, consider this linear function over this line. It is still a linear function. Over a segment, we have a linear function. It is increasing in one of the directions. It might also be not increasing, it might be flat line. Could have. But anyway, if it is increasing, I'll just move in the direction of increase, let's say to here. If it is a flat line, well, I still am free to move in one of the directions. It will just not change the value of the objective function. So whatever happens, it is still a good idea to move to one of the directions. Well, and now I'm at a corner. At the corner, I don't have any further arguments. But at the corner, I already pushed two of the constraints to their maximum. In this case, this one and that one.
Does that work? So, depending on how many, like what space you're in, you push that many constraints necessarily then?
Yes. So we had one observation like this. Second observation is indeed that, yes.
I just wondering, when you're pushing the constraints, it makes sense if it's a positive slope because they're both increasing as you're going. But if it was a negative slope, like the x1 plus x2 is less or equal to 9, as one variable increases, the other variable decreases, right? So how can you be sure that as you decrease more, how can you be
So
sure it's
suppose
not
I am
there?
right
Yeah.
here. So as I go to one of the directions, indeed one of the variables increases, the other one decreases, and the opposite direction is the opposite way. But anyway, on this line, I can consider this function. This function is also a linear function. If you consider the graph of this function over this segment, it looks like this, or like this. In either way, well, it's increasing in one of the two directions. If it is increasing in this direction, I will push my point to this side.
What
The
if
function will
what if instead we weren't looking for the maximum of 3x1 plus x2, but we were looking for the maximum of x1 plus x2?
Okay, if I were looking for a maximum of x1 plus x2, then, well, I will go and push this constraint. On this line, x1 plus x2 is 9 at all points. So the graph of my function looks like this, it's flat. Okay, so I do have an optimal solution right here, but I also can push it to any one of the directions, either to here or there. And then I'll find an optimal solution here, well, and also an optimal solution here. So in any case, if I want to find an optimal solution, not
I
all
push
of
to
those.
the constraints, yeah.
I'll
So
just push.
there are cases where there are more than one optimal solution and they're not necessarily on the, you don't have to push to the constraints.
Yes, exactly. So what I'm trying to explain is that regardless of what the function is, I can always push as many constraints as I want. It might not always be necessary. Exactly in your example, when you are trying to maximize x1 plus x2, well, I will have kind of two optimal solutions where I push two of the constraints to their limits, but I also have several in between. But every time I will have an optimal solution inside, so I will be able to push it to one of the corners. It could be even worse. I could have tried to maximize a function which is 0 times x1 plus 0 times x2. This function is constant all over the region. And then an optimal solution will be here, will be here, will be here. But anyway, it is the same value of the optimal of the objective function everywhere, so I am allowed to push to one of the corners. So anyway, if I'm just trying to find one optimal solution, well, it makes sense for me to look just at the corners, to push as many constraints as possible to their limits. Next observation, as you said, well, how many constraints? So how many constraints? Can be pushed to their limits? Well, linear algebra tells you the answer. If you have n unknowns and you want to get just one point, well, impose n equations. So as many as the number of variables. This is the second observation. And third observation, well, how many calculations we'll have to perform? How many calculations we will have to do for the system with, say, two variables, 5 constraints. Like in our case, well, we'll have to choose 2 constraints out of 5. The number of choices is, well, we choose the first constraint out of 5, we choose the second constraint out of 4 remaining ones, and it didn't matter in what order we chose. So 5 times 4 divided by 2, which is 10 constraints. 10, 2 by 2, linear systems. So using this method, we'll have to solve 10 2x2 linear systems. Let's see what happens if we have n variables and n constraints. Well, it will be slightly worse. I mean, depending on n and m. You want to choose n constraints out of m. Well, there is a standard notation for how many choices are there of n objects out of m. It's called the binomial coefficient, n out of m. And you want to solve n out of n, n by n linear systems. Okay, so we have a way to solve now more or less any linear programming problem, and the algorithm is as follows. Look at your problem, look at all the constraints, decide how many variables do you have. Well, once you decide that you have n variables, choose all possible systems of n constraints out of these m constraints, replace the inequalities by equalities, solve the system, and well, make a table with that many entries. For each one of those, check whether the solution is feasible, which means well, n of the constraints are satisfied by equality signs. What happens to the other ones? Are they satisfied? Out of those, we'll find the largest value of the objective function. Okay, so this algorithm does work. Unfortunately, it is not practical at all. This number, m choose n, is huge, well, in typical applications. So in a typical application, we might have, say, 200 constraints and 100 variables. This algorithm, even a computer, will not solve it, even a good computer. It is so on its own. Well, let me just say that it's a huge number. So what is it? It's about well, it's somewhat like 100 to the power 100 kind of systems. So it's really not practical. Okay. So then we'll have a different data. So what was wrong with this idea? Maybe let's draw a picture. We have a region which is just a pentagon, like this. Well, slightly different one, like this, and like this. So we have a pentagon. Actually, it has only 1, 2, 3, 4, 5 vertices. So if we could just look at the vertices, we would be able to go over just 5 points, 5 systems of linear equations. Unfortunately, we also will make some of the kind of stupid calculations. This one, that one, and there should be this one, and one here. So once we push 2 of the constraints, we have no idea whether we land in a feasible region, somewhere here, or outside, somewhere here. And that's why we'll have to go over a huge amount of linear systems and solve each one of those. Another idea which we will pursue is like this. Well, it's quite easy to find, well, at least in our problem, it was quite easy to find one feasible solution. In fact, it was a solution right at this corner, 0, 0. Now let's try to increase our objective functions. So the algorithm will proceed like this. I have this point, At this point, my objective function is, well, not likely to be the largest one. So let me consider, let's say, this edge. Along this edge, my objective function, well, is either growing or going down. Well, if it's growing, I'll push from here to this point. We'll see how to do this algebraically, but the idea will be like this. If my function is increasing along this edge, it will push the point towards the next vertex. If it is decreasing, well, I will not touch this edge. I will also consider then this edge. If the function is increasing along this one, well, I'll push in this direction. If it is decreasing along both directions, I have an optimum. That's once again some kind of linear algebra consideration. Okay, if I manage to push to a better solution, a solution with a better value, larger value of objective function, I'll repeat my procedure. I will not consider all possible points, I will only consider, well, now I have just one way to go. I'll consider whether going in this direction will further increase my objective function. Well, if it does, I'll move to this point. If it doesn't, I stop here, that's my optimal solution. Next part, well, I'll go in this direction. And repeat. So this way I will have to solve at most 5 systems of equations. And that's exactly what we will do. So that's the idea. Well, in a picture, without any calculations, unfortunately, we will have to actually perform the calculations, and we will also have to perform these calculations not with just 2 variables sometimes, but with 3, 4 variables by hand, or 100 variables on the computer. So we'll have to learn how to do this algebraic procedure without referring to the picture. Okay, so before I go to the actual algebraic calculation, maybe any questions about this picture or the idea in general? Okay, so
最理想的可能是这个一个，但是如果这个不是的话，就分这个；如果这个不对的话，就这个。但是像这个进行这个就是如果说它这个有，如果这个没有这个的话，那就
okay, guess we'll have enough time just to push the solution along one of the edges, but let's do it as this. So algebraic version of the pushing along edges algorithm. So we'll proceed in the following way. I want to maximize, let me give a name to my objective function, I'll call it Z. I want to maximize this linear function, 3x1 plus x2, subject to the following constraints. Now let me rewrite these constraints in a little bit different way. I want to know at each step how much I actually push the constraints. So I'll introduce some new variables. x3 will be this variable. It will be 2 minus x1 plus 2x2. So the value of x3, the meaning of x3 is how much the first constraint, this one, x1 minus 2x2 is smaller than 2, is pushed to its limit. Once x3 is equal to 0, I know that my constraint is at the very limit. If it is bigger than 0, well, I still have room to push. And I'll introduce such variables for each one of these constraints. 11 minus 3x1 plus x2, and x5 will be 9 minus x1 minus x2. And I want, well, what do I want? I want x1 to be positive, x2 to be positive, and I also want the inequalities to be satisfied. They are just x3 is positive, x4 is positive, x5 is positive. So I just introduced new variables whose meaning is just to what extent the constraints are pushed to their limits, and I rewrote the problem in this way. It looks now a little bit more symmetrical. Now I have 5 variables, they're all positive, and I have some equalities. Let me just introduce a name. These variables will be called slack variables. So, as opposed to x1 and x2, which are important for my kind of decision, for my schedule, for my problem, these ones, well, are not that important. They're just a convenience for me. Next step. So right now I am at this point, 0, 0. I want to push my linear function along one of the edges. And what are the edges? Along one of those, x1 is equal to 0 and x2 is broken. It's this one, x1 is 0, x2 becomes larger. The other one is x1 is 0 and x2 is becoming larger. So, I look at my objective function and I see the following. If I keep one of the variables 0 and the other one is increasing, my objective function will grow, regardless of what variable I choose to increase. Okay, so let's keep one of the variables 0 and let the other one increase. Which one is better to keep at 0 and which one is better to try to increase? Yes, it looks like the coefficient of x1 is 3. So for every unit of increase in x1, I'll increase the objective function by 3. If I make the alternative choice and I keep x1 0 and increase x2, well, for every unit of increase in x2, I'll increase the objective function by just 1. So maybe it's a good idea to keep x2 equal to 0, increase x1. So I decided that I want to keep x2 equal to 0 and increase x1 because my function is growing quite fast along this direction. Well, to what extent? I want to increase it as much as possible, but definitely I don't want to go out of this feasible region. I still want all the other variables, x3, x4, x5, to be bigger than 0. Well, let's see. If I increase, so I keep now x2 equal to 0, I increase x1. The first variable here, 2 minus x1 being bigger than 0, this inequality tells me I can increase x1 at most up to 2. So I can increase up to 2, and this from x3 being bigger than 0. Well, other inequality tells me other thing. So up to 11 over 3 from x4 being bigger than 0, or up to, well, all the way up to 9 from x5 being bigger than 0. So the constraint that x3 is positive tells me you can increase x1 only up to 2. The other constraint tells me you can increase x1 only up to 11 by 3. And the last one tells me you can increase x1 only up to 9. So which should I listen to? They tell me 3 different things, which should I listen to? Well, the answer is I want to listen to all of them. And the one which is the strictest, which tells me, well, don't do this and this and this and this, well, is the first one. you want to increase x1 only up to 2. Once you increase it only up to 2, well, automatically you did not increase it all the way up to 11 over 3 or all the way up to 9. This is a little bit bigger than 3, but this is, well, 9. So this one is the strictest. Well, in my new attempt, new solution will be x2 equal to 0, x1 equal to 2, and, well, I did increase the value of z. Z is now 6. So I pushed from this point all the way to this point, 2, 0. Okay, so we'll have to stop right now, and we'll see you next time what happens next. See you.